So in the past, applications were housed in single private data centers, potentially 2 data centers for high availability. These data centers were on premises, and all components and standard applications were housed internally. So we have simple applications consisting of a few tiers that were housed in standard data centers. As a result, troubleshooting and monitoring was relatively easy to do. The network and infrastructure were pretty static, and the network and security perimeters were well known. There were only a few entry points to the application stack, and generally there were only a few ports open to the external world. More importantly, there weren't many changes to the stack. You may have made a change only once every few months. There is a joke saying that the most stable application is the one that nobody makes any changes to. However, we live in a completely different environment today, and changes are made to applications every single day. Previously, with the traditional style of applications, they would fail in very predictable ways. As a result, it was relatively easy to monitor these types of applications. When you can no longer predict what is going to happen, you can no longer rely on a reactive approach to monitoring and management. Today's distributed applications now fail in very creative ways. As a result, we need to move towards a proactive approach to monitoring. Microservices applications are distributed and susceptible to a number of external factors. On the other hand, if you examine a monolith, all the functions reside in the same process. So if there is a failure, the application as a whole will fail. This resulted in predictable failures. We had a very binary approach, and it was usually up or down, and with some basic monitoring in place, this was easy to detect, as failures were predictable. But once the monolith is broken into a microservices-based architecture, a request made from a client can go through multiple hops of the microservice, and we can have several problems to deal with and unpredictable failures. We have distributed microservices applications with components or services located in many different places. Some modern applications could be in multiple clouds and different location types, all done simultaneously. As a result, there are multiple data points to consider and potentially troubleshoot. There is growing complexity of the infrastructure, and let's face it, a lot can go wrong. So it's imperative to have a global view of all the infrastructure components and a good understanding of the application performance along with its health. Distributed computing has a lot of components and services. With these components could be quite far apart. As a result of the distributed nature of modern applications, latency can add up. And we have both network latency and application latency. The network latency is several orders of magnitude bigger. As a result, you need to minimize the number of round trip times and reduce any unneeded communication to an absolute minimum. When communication is required across the network, it's much better to gather as much data together to get bigger packets that can be sent more efficiently. There are many moving pieces and parts in a large-scale container-based application design, and manually validate each piece health is going to be hard to do. Therefore, monitoring and troubleshooting are an awful lot harder, especially as everything is interconnected, making it difficult for a single person in one team to fully understand what is going on. The core challenge is trying to debug a microservices application. So a lot of our tooling today has been built for the traditional monolith application. So there are new monitoring tools for these new applications, but there's a steep leaning curve and a high barrier to entry. For this, you need to understand practices like chaos engineering and how it can improve the overall reliability of the system. Chaos engineering is the ability to perform tests in a controlled way. Essentially, what we're doing with chaos engineering is breaking things on purpose to learn how to build more resilient systems. So we are injecting faults in a controlled way to make the overall application more resilient by injecting these faults and understanding application behavior. And this testing should be done in a controlled manner, so we are not waiting around for errors or problems to occur. We are purposely creating them in a controlled manner. Chaos engineering is all about creating experiments that can break things in controlled environments. Essentially, we are finding weaknesses in a system before they become critical issues that may affect the entire business. It's not something done at random, and it is used when you want to have something carried out under strict circumstances. So how do you start all of this? The recommended starting point is to understand your baseline and the acceptable conditions that the application works in. For this, you should determine where and what are the possible breaking points in your application and what parts of your application are most likely to fail. For example, you need to understand normal latency and what is the normal transaction rate. Once we have this, we can start to see deviations. But without a good baseline, you won't know what's good or bad. Then we need to find the breaking points. To find the breaking points, we need to put the application and the infrastructure it lies on under stress. When the application is stressed, it will start to break, and different parts of the application will break depending on the stress level they're exposed to. So here we can ramp up a single instance of the application until it gets to a point where it can't service any request or it completely breaks down. And as you witness the service heading towards breaking point, you should be tracking all possible metrics to determine the patterns, as this will be used to give you useful insight to how the application and its surrounding environment are being infected by the fault. Finally, we need to test for resilience and find the code's resilience. Once we know the application breaking point, we can lower the load and observe how the application starts to recover.